Good evening, everyone. Welcome to this 11th session of problem solving. So we'll have some discussion on probability and statistics. So I had planned for traffic flow also, but I think if you have more questions in probability and statistics, we can stick to this alone. Towards the end of the session, we'll also look at some problems in random variables. So the plan for today is we'll look at discrete and continuous random variables. We'll look at some of the common probability distributions. In GATE exam, we'll be getting only two main distributions. One is the Poisson distribution, and the other is the binomial distribution. Then we'll also look at a little bit of statistics. This is not that important from a GATE point of view, but it is sometimes questions are being asked. So this maybe we can take it up in the next class or towards the end of today's class. So that's what it is. And but there's an important topic in GATE. Almost every year there are at least 2 to 3 questions from traffic engineering. So we'll go through it later on. And as we discussed in the last class, the reference for the math part, probability and statistics is Kreyszig's Advanced Linear Mathematics. It's a good. It deals with probability at a basic level. So this is a good read. Just to recap what we did in the last class, the last session. So we looked at methods of sampling, the measures of average, which is the mean, median, and mode, and also the spread, which is variance. Then we looked at the theorems of probability. So first, we thought we looked at two different ways to. So these are the basic terminology associated with the probability theory. So what is an experiment, trial, outcome, and these are the basics. So we also looked at how to define probability in terms of equally likely outcomes. That is, if a random experiment has got equally likely outcomes, then we define the probability of an event as the number of outcomes in the event A divided by the number of outcomes in the sample space. But this doesn't work always. So we also looked at the relative frequency type of definition, where we perform a trial very large number of times and we see how many times the event occurred divided by the total number of trials. And what takes care of both these definitions was the axiomatic definition that probability is treated as some function. So you take an event and assign a number to the event. The number has to lie between 0 and 1. And the probability of the sample space has to be 1. And for disjoint events, it follows the addition law. So this is what we discussed in the last class. Then we also looked at the problem of conditional probability. So given two events, if the outcome of one event does not affect the outcome of the other event, the probability of the other event, then they are said to be independent. But under some conditions, suppose under some conditions, we know that if the outcome of one event is known, then the probability of the other event is affected by that. So that probability. So therefore, since we know the power B has occurred, B acts as a reduced sample space. So initially, the set of all possible outcomes is the sample space. But if I tell you that B has already occurred, then it means that the set of all possible outcomes is only those that are contained in B. So B acts as a reduced sample space. So instead of dividing by 1, which is the probability of the sample space, we divide it by the probability of B. And what are all the events possible? Now the events probability of A condition B is those events that are common to both A and B, because events that are not in B but are in A still cannot occur because we know that B has occurred. So this is how we define conditional probability in the last session. And then that the condition for independence of two events follows immediately. So independence means the fact that B has occurred should not affect the probability of occurrence of A. So what did we do? We said probability of A condition B should be equal to probability of A, in which case probability of A intersection B will be nothing but probability of B multiplied by probability of A. So this was the condition for independent events. Then this is where we stopped the last session at. So we looked at permutations and combinations. These are useful in problem solving. So n distinct things taken all at a time is n factorial. Suppose there are some of them. Suppose there are m classes of equal things. then the number of permutations all taken at a time is n factorial by n1 factorial, n2 factorial, up to nm factorial, where n1 are identical, n2 are identical, and so on. And only k of them taken at a time. So when we look at only k of the n distinct takes taken at a time, we know that the number of permutations is npk, defined as n factorial by n minus k factorial. And if repetitions are allowed, we saw it is n power k. That is, the same item can be repeated in multiple spots. And finally, we also looked at combinations where the order is not important, then it is nck. These are useful in problem solving. We'll solve problems today. So today we are going to look at random variables and other parts. So before that, there was one question in the chat box of in the group Google group. So I think Dharani asked that question. Is that okay? Could you
Yes, sir. I understood, sir. I
yeah,
learned from the document,
okay,
uh, and I solved those problems given, sir.
okay.
Sir, is that correct or not? How come I know, sir? Can I
We
post my
can
answers?
yeah. Let me open the document. We can have a discussion right now. It will take just 5 minutes. So it is in page. Yeah. So I hope the others have gone through this as well, because it's not directly available in a textbook. So I just made this. So the conditions are this. This is okay. For some context, in case you hadn't looked at the email, it is to examine the stability of a structure, to classify structures as stable or unstable. What is the procedure we go through? So so first I describe what are the conditions under which a structure becomes unstable. Either the constraints are not enough or the constraints are not correct. If the reaction forces are such that they are concurrent at a point, the structure is unstable. And if the reaction forces are parallel, they are unstable. But this is only external instability. A structure can be internally unstable. And for the conditions for internal instability for frames and trusses is that you identify all the unknown, you divide the structure into some number of components, look at each component one at a time, identify all the unknowns in the structure, and write down the equilibrium equation for so each independent component will have 3 equilibrium equations, and if you have fewer unknowns than the reaction than the equations, then we cannot get a solution. We cannot get an equilibrium solution, which means the structure is unstable. Not only that, if for any of the components, if the unknown forces are either parallel or concurrent, then that individual component is unstable. Therefore, the structure is unstable. When it comes to beams, since the horizontal forces do not cause any moment at all because they are all passing through the axis of the beam, they are completely separated from the vertical forces of the bending moments. So the condition for beams is that you look at the horizontal forces have to satisfy the stability condition separately, and the vertical forces and the moments have to satisfy the condition separately. So Rx should be less than n, and the total number of forces, unknown forces minus Rx, should be less than 2n for the condition of instability, not condition of stability. So if any of these conditions starting from 1, 2, 3 up to 7, if any of these is satisfied, then the structure is unstable. If none of them are satisfied, then the structure is stable. But the trick is that in most cases, you can just draw the deformed shape and determine if it is stable or unstable. So this was the question that Dharani had asked in the forum, and I have solved it. So then I have given some more questions to look at. So maybe we can look at the answers right now. So where can I write? Let me put it here. Okay, so look at the first structure. So those who have solved, you can answer. What do you think this is? Is it stable or unstable?
Stable, sir.
Stable. Okay, let us examine that. So the structure is, you have this. Here it is a rigid link. Here you have an internal hinge. Here you have, I think it's a hinge support. Let us call it A, B, C, D. So this is a frame structure. This is an internal hinge. By inspection, let me tell you, by inspection, if I apply a vertical force here, what will happen? Right? If I apply a vertical force here, this is free to rotate. So this will go up. This will go here. Yeah. And this will cause this member to get extended. So it is most likely stable. So let us solve the problem. We have, so the structure as it is first thing is external. If you look at this, you have two forces here. They are neither concurrent nor parallel. So externally, we have four forces, which is greater than the number of equilibrium equations, and they are not concurrent or parallel. So externally, it is stable. Internally, if we look, we have to look at these two structures separately. We look at this, look at this. Here we have two unknowns. Let us call it AX, AY. Here you have CX, CY. Here you have equal and opposite. Don't write new unknowns. Here you have CX and CY. And here we have DY, DX. How many unknowns we have? We have 1, 2, 3, 4, 5, 6. And the number of components is 2. So R is equal to 3n. Therefore, it is stable. So your answer is right. The structure is stable. R equal to 3n. Only if R is less than 3n, it is unstable. Looking at this,
Sir, by inspection, but the structure will move, no, sir, if a small force is applied.
yeah, the structure will move. It cannot form a mechanism. For example, let me put another case where this is in the same plane as this. Right? I am just removing the bend and putting A, B, and C. Now, if I apply a vertical force, what happens is this is free. This is kind of free to move. This structure is actually unstable. But this structure is stable because when this acts as a rigid link, when this rotates, say it rotates by a small delta theta, take this point, right? This point will have both horizontal and vertical displacement. So the horizontal displacement is restrained by this member. On the other hand, here, if you apply a force, the horizontal member is not restrained. There is no horizontal force generated. If you undergo really large displacement, this member will start stretching. But in the linear elastic case, when we apply a small vertical displacement, this will rotate freely. This will rotate freely. Therefore, this structure is unstable. But if you give a bend like this will rotate. You're right. This will rotate, but it cannot rotate freely because there is also a horizontal displacement that's induced when this member undergoes a rotation. So that is the difference between this frame and a beam. It will not rotate freely. So by inspection, if you see, this is the structure you have. This, for simplicity, you can treat them as axially inextensible. So if this deformation has to occur, then this member has to extend a little bit. By how much? It has to extend by, suppose this length is A, this has to extend by delta x equal to A times delta theta. And if A times delta theta, it is extending, this point is hinged, right? So if it is extending, it will resist the force. It cannot rotate freely. Similarly, you can also check the other, you can apply a small horizontal force and the same thing follows. It cannot rotate freely. But here, that is not the case.
Okay, sir.
Is it okay?
Understood.
Yeah. Here, if you apply a vertical force, it just, the vertical displacement is, say if this is L, vertical displacement is L times delta theta. Horizontal displacement is still 0. And this force is applied, so this will just rotate freely. But here the case is different. That is why there is this difference in formula between beams and frames. So is that okay?
Yes, sir.
Yeah. Now look at the second structure. So what do you think? This is very similar to what we had in the exam, but is it stable or unstable?
Stable, sir.
Yeah, it is stable. The reason this is stable and this is not unstable is Again, by inspection, you can see that the collapse mode here is this is going downwards. If you apply a small vertical force, this is going downwards. But here that cannot happen because you're restraining this from going downwards. So here this, of course, externally it is stable. You have 1, 2, 3, 4. Four reactions and 3 equilibrium equations. So it is externally stable. Internally, same analysis you can do. Look at this separately. Look at this separately. Look at this panel separately. You're replacing the member. You're replacing these two members by their axial forces because they are two force members. The forces will be equal and opposite. So you have one FFE, you have FAB. What all other unknowns we have? Here we have the these two AX, AY, and here you have the BY. Here we have CY, DY, DX. Sorry, DX. So 1, 2, 3, 4, 5, 6. We have 6 unknowns, and it's a truss. So R is equal to 6. We have taken 2 parts. So R is equal to 3n. So that is stable. What about this structure? This is a tricky one.
Unstable, sir.
Yeah. Why is it
Forces
unstable?
are concurrent.
Yes. If you are,
Concurrent.
yes, correct. That's good. That's a good analysis. So you take here you isolate. Of course, externally it is stable because 3 unknowns and 3 equilibrium equations. Internally, you take these two separately, A, B, C, and PQR separately. And here the unknowns are like this. You have an AX, AY, BY. And you also have the internal unknowns. Let me denote them by red color. So you have a tensile force here, tensile force here, tensile force here. This panel is stable because the forces are all forces are not concurrent. These 3 forces are concurrent. That is okay. But you also have non-concurrent forces which will satisfy moment equilibrium. But this panel, if you see, all the forces are concurrent. You assume tension. This is FCR, FAP, FBQ. And all these forces are concurrent at the point O. So by inspection also, you apply a small, we can apply a small force like this, right? We can apply a small force like this. What happens? This will rotate freely. It will rotate freely. So this stress is unstable. And what about this stress?
Stable, sir.
Yeah, this is stable because precisely whatever problem is there here, that problem is not here. Here they are not concurrent. Otherwise, you can see this has got how many unknowns? This has got 6 unknowns and 6 equilibrium equations. So this is stable. Here also you have 6 unknowns and 6 equilibrium equations. In addition, the forces are not concurrent. So this is stable. And what about the last one? Sorry, E.
E is unstable, sir.
E is unstable, correct. So what is the mechanism? By inspection, you can say you apply a small force here, say delta P. What will happen? This will rotate freely. This is a rigid link. So what will happen? This here you can have here you have to have 0 displacement. So this can go up. This can rotate as well as this can also move upwards. So if uh, if the vertical movement is prevented, the structure is stable, but this will just move upwards. So this is the mechanism it forms. Again, in terms of the unknowns, so externally it is stable. You have 1, 2, 3, 4, 5, 5 reactions and 3 equilibrium equations. So externally it is stable. Internally you can draw. So 1, 2. At 3, B you have 3, 4. In this we have already accounted for B. So you have 5, 6, 7, and here you have just a minute. So we have 1, 2, 3, 4, and here we just have these two. We have moment and horizontal force. So this structure is you have got 1, 2, 3 individual parts, and 1, 2, 3, 4, 5, 6, 7. Okay, wait a minute. Something is not correct here. So these are equal and opposite. Here you have an external force. this is supposed to be unstable, but how come it? So we have ax, ay, bx, by. This is again bx, by, cy, dx, dy. This is moment at E, and this is Ex. And this is a frame structure. So R equal to the number of unknown reactions is 1, 2, 3, 4, 5, 6, 7, 8, 9. How come this looks stable?
Sir, there are, yeah, n is equal to 4, no, sir.
Okay, did you separate these two? So if you have separated this, so if this is one way, if you do it AB as one, BFC as the other, and CD as the other structure, and DE as the other structure. So how did you do n equal to 4?
Sir, I divided this into 4 stable
4.
components. Sir.
Okay, AB is stable.
Then
BF,
BC.
BC,
Then
okay,
B.
BFC. Okay, fine, this is stable. CD is stable, and DE is stable. Okay, fine. So fine, the answer will not change mostly. So if it is AX, AY, at B, what do we have? At B, we have BX and BY. So here you have just equal and opposite. At F, we have nothing. At C, you have uh, CY, CX, and you'll also have a moment because that is an internal support, right? You'll also have a moment MC. They said you should also denote MC. So here CY will not be the same as the CY on this side because of the additional hinge. So let us call this CY1 and CY2. And then we have CX. CX will be the same. Here you have DX, DY. Here you have DX, DY, DX. And this side is same thing, EX and ME. So the number of unknowns are 1, 2, 3, 4, 5, 6, 7. Here you have 8, 9, 10, 11, 12. So I have 12 unknowns, and we have 1, 2. So 4. So 3 fours are again 12. So this structure is stable actually. So,
Sir, I forgot to apply that moment on C, sir.
yeah. That's a common mistake because it is an internal intermediate support. There will be a moment here. In fact, the moment will be, if you draw the bending moment diagram, you'll have something like this. You'll have a peak here. So there will be a moment that will be equal and opposite. Not only that, unlike a hinge, in a hinge, the left side shear force is equal to the right side shear force. But if you have an intermediate support, you know how the shear force diagram looks, right? So the force on the left span is different from the force on the right span. So that you need to separate into two different, because the condition for equilibrium is Cy2 minus Cy1 is equal to the reaction force at C. So that you need to consider. So this is a stable structure. Whether you divide it into 4 or 3, this is a stable structure. So yeah, so that is fine. Now last one.
Stable, sir.
Last one is stable. Let us see. I don't remember the answer, but so here externally it is stable. We don't need to check that. Internally, so AB is a stable component. BCD is a stable actually BCD. This entire thing is a stable component because it is rigidly connected. So you can take this AB, BC, D, E, G. You can take EF. So at A we have vertical and horizontal forces AX, AY. At B, we have, say, Bx, By. Here they are just equal and opposite. At G, you just have a Gy. At E, we have Ex, Ey. And here they are equal and opposite. At F, we have Fx and moment N. Now let us see. So how many unknowns we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have three parts. So 1, 2, 3, three equilibrium equations per part. So this is a stable system. So these two are this is unstable. Everything else is stable. So fine. That is the procedure. Let us get into today's session. So that's okay, right? You got the idea.
Yes, sir.
Yeah. So let's get back to this. Yeah, we are already halfway through. Any other doubts? Anybody else has any doubt? It was okay, right?
Yes, sir.
So this is where we stopped last time. So let us proceed from there on. We have seen. So we have seen the condition for. We have seen. Or maybe we can start with. Okay, so probability. So far we have seen. We have seen a sample space. We have seen outcomes, which are the elements of the sample space. So sample space S is a set, and it has number of outcomes, say outcome 1, outcome 2, and so on. Event E is a set of outcomes, and say OI, OP, and so on. And event E is a subset of the sample space. And probability is a function from the sample space. Actually, not the sample space. It is the set of all subsets of the sample space. So mathematically, I'm not sure if you know, that is called the power set. So set of all subsets of a given set is called the power set. So you take every event in the power set of S and assign a real number between 0 to 1. That is called the probability function. So this is what you have seen so far. To make it more mathematical, there's an intermediate step. So that is the concept of random variables. So what we do in random variables is that you map from the sample space. So from the sample space, you have events, and say you have the real line. The real line from minus infinity to infinity. Corresponding to every outcome, suppose the outcomes are discrete, corresponding to every outcome, we assign one real number. Say that real number is x. So x is a real number that is a function of every outcome. So if you take one outcome and assign a real number x to that outcome, that's all. So if you take our experiment of tossing a fair coin, you can have one time. So toss a fair coin one time. You can have head is an outcome, tail is an outcome. So corresponding to head, I can assign x equal to 0, and corresponding to tail, I can assign x equal to 1. So x is a function of the outcome. So x is a function from the sample space. Sorry, sample space I'm denoting by S0 to the real numbers. That's all. And such a function is called the random variable. Until now, what we were doing is we take the sample space as it is. We take every outcome and assign one number between 0 and 1. That is called the probability. Here, instead of doing that, we have an intermediate step. You assign a number to every outcome, and for that number, you decide some probability. So random variable is a function. So the random variable is a function defined on the sample space of an experiment, such that its values are real numbers. So x is if we say x is a random variable, then x of every outcome is a real number A such that the probability of x equal to A is defined. So basically we say that if you take an so random variables is such a function which takes in, so right, function is something you take a set one. Yeah, this is basic what we study in 11th and 12th standard. You take the elements of one set and assign it to the elements of other set in a unique manner that we call it as a function from S1 to S2. So this is the function which you study in sets, relations, and functions in class 11 or class 12. So you take every element of set one and associate to every element of set, not necessarily every element. You take an element of every element of S1 and associate it uniquely to an element of S2. We call that as a function from S1 to S2. Similarly, our sample space is a set. Our real number is another set. You take every outcome in the sample space and assign a real number such that the probability of that real number being or the probability of so you if you assign a number A to an outcome, the probability of that number should be defined. That's all. And this is for discrete. If the outcomes are discrete, you call this is the condition. So for every outcome, you have a real number, and the probability of the random variable being equal to that real number should be defined. Should be defined means it not necessarily has to be greater than 0. It can be 0 also. It should be something. It should be defined between 0 and 1. And if it is a continuous case, we'll see what is continuous case and discrete case shortly. If the probability of x, the random variable belonging to some interval which is a subset of the real line, should be defined. That's all. So I will see with examples. So let us look at the coin tossing experiment. So for the coin tossing experiment, what do? We have the outcomes head, tail. If you toss one coin. So to this, I can assign the random variable of head is equal to 0 and the random variable of tail is equal to 1. Now, what is probability of x equal to 0? The probability of x equal to 0 is, if it is a fair coin, it is 0.5. Probability of x equal to 1 is what? It is 0.5. What is the probability of x equal to 0.5?
0, sir.
0. So we have defined the probability this way, such we have defined the probability function. So now probability function is a real valued function, right? Earlier, so there are two functions here. One is the random variable function, which takes in an outcome and returns a real number. And now we have another function called the probability function or the mass function. We can put an M, probability mass function, which assigns a real number to, which assigns a probability to every real number. Similarly, probability of x equal to 2 is also 0. So this is the first example. Let us take the next example where we toss two coins. So the sample space, what is the sample space? You can have head and head, head and tail and head, tail and tail. Now I can assign a random variable to each of these outcomes. So corresponding to head and head, let me assign 0. Corresponding to tail and tail, I can assign to this I can assign 1. To this I can assign say 2. To this I can assign 3. This is one way of defining a random variable. This is very discrete. So what is p of x equal to 0? It is 1 by 4. P of x equal to 1 is 1 by 4. Similarly, p of x equal to 3 is also 1 by 4. So this is let us call this random variable x, right? I can also define a random variable. So I can also define a random variable y, which is equal to the number of heads appearing. Now, corresponding to every outcome. What is the random variable y? If it is head, y is equal to 2. For head-tail, y is equal to 1. Tail-head, y is equal to 1. And for tail-tail, y is equal to 0. Now, what is P of y equal to 0? This is the probability mass function. P of y equal to 0 is
1 by 4, sir.
1 by 4. Probability of y equal to 1 is
1 by 2.
1 by 2, because there are 2 and there are equally possible outcomes. So you can say it is 1 by 2, 1 by 4 plus 1 by 4, it is 2 by 4, which is 1 by 2. And probability of y equal to 2 is.
1 by 4.
So these are two different random variables. Now here, so this is how we define a random variable. Here the outcome is either head, tail, head, or tail, tail. But to each outcome, I'm assigning one number, and that number doesn't have to be unique, as you see, right? A function can be like this. This is called an onto function, right? So in the first case, it is a bijective function. Corresponding to every random variable, we have only one outcome. Here it is here is a many one function. Many elements are mapped to one element of set. So these are discrete cases where we can count the number of outcomes. We can count it, right? You can see these are discrete outcomes. Now let us look at another. Let us look at another case where I'm throwing. So suppose I'm standing on top of a building, and below there is some ground. And say we are dividing it into 4 parts. And suppose we throw a stone or something from the top. The stone can land here, can land here, can land here, can land here. It can land in any one of the 4 squares. It can land, right? It can land, basically it can land anywhere in this region. Suppose there is wall or something, it can land anywhere here. So suppose this square goes from -1. So suppose the x coordinate of the square, or rather, let's not have this. Let there be a person here. And this person is standing on some ground. Suppose he's throwing a stone at random, not focusing on anything. So the stone can land here, it can land here, it can land here, it can land here. So the stone can land here, the stone can land here, it can land anywhere basically. So the distance at which it lands, let it be x. And of course, because we know the person cannot throw very far away, so if you say x equal to 10 meters, it has got some probability. So there is some probability that the stone can land within 10 meters. But if you say x equal to 200 kilometers, then obviously the probability of x being greater than 200 kilometers is something, it's almost zero, right? It's very close to zero. Or we can even set it equal to zero. A person cannot throw a stone that far. Now here, what kind of random variable x is? Now I'm defining a random variable x, which is the distance at which stone lands. So this is another random variable, and corresponding to every x, is there a probability? So I can say with certainty that. Now what is the sample space? The sample space is not discrete right now, right? The sample space is what is the sample space here? Can anyone tell what is the sample space? So x is the random variable from where the experiment. The random experiment is throwing a stone and measure the distance at which it lands. So what is the sample space? What are all the possible outcomes?
0 to infinity.
Correct. It is all numbers possible from 0 to infinity. It cannot be negative, of course. We are only looking at the absolute value of these things. So the correct answer, as you said, it's perfect. It is the sample spaces. If you treat the outcome as the distance, then the sample space is 0 to infinity. And the random variable, we can define it as the sample space itself. Right? These are also numbers. We are also interested in numbers. So the random variable also can belong to 0 to infinity. Now, this is a case of continuous random variables. Why is it continuous? Because we cannot, the number of possible outcomes is not finite, it is not countable. So even if it is infinite, there is countably infinite and uncountably infinite, right? So if I say the stone can land at 0, the stone can land at 0.1, the stone can also land at 0.01. And if I say the stone can land at 0 and 0.01, you can always find a number in between two, two different outcomes, right? If you say 0.0001 is an outcome and 0.0002 as another outcome, you can always find an outcome in between the two, no matter what. So this is a case of continuous random variable where the sample space is continuous, and so is the random variable also. Random variable. So in these cases, so these are the two different cases. So that is the idea. So random variables, you can divide, we can classify them as, so random variables can be, so we have defined what random variable is. Random variable is a mapping from the sample space to the real line. It can be either discrete or continuous. Okay. So when the random variable is discrete, uh, so let us look at, discrete random variables first. Yes. So first case is discrete random variables. So as I said, the random variable assumes only countably many values. You can count the values. So the random variable x assumes countably many values. Countably many means I can say x equal, after x equal to 0, x equal to 1 is the next random variable. After x equal to 1, x equal to 1.5 is the next random variable. It's not that if I give two values, you can always find an outcome which is lying in between the two. That becomes uncountably many. So it assumes countably many values. X can take only countably many values where x equal to x1, x2, and so on, such that they have non-zero probability, such that p of x1 is not, yeah, they have non-zero probability. So there are only countably many values whose probability is non-zero. So for discrete random variables, as I said, we have something called the probability mass function, which assigns a probability p to uh, random variable. So this is the set of all possible random variables, values of the random variables for which the probability is greater than 0. So p of xj is equal to p. That is what it means. So the random variable takes only countably many values for which the probability is non-zero. And those non-zero values are, say, pj or something. So this function, so this is called the probability mass function. So the probability mass function is a function from the real line to 0 to 1. What it takes a real number. What is that real number? It is the random variable. And if it is discrete, it is the random variable doesn't take all real values. It takes a discrete, a countably many number of real values for which the probability is non-zero. For other real numbers, the probability mass function is 0. Very related to this is the probability, the distribution function. Probability distribution function. which we denote as capital F of X. Let me put a small x. It is defined as the probability of the random variable being less than or equal to X. That's all. So the probability distribution function is defined as capital F of X, which is nothing but the probability of the random variable being less than or equal to small x. So let us again look at it with an example. In the case of coin tossing problem, so we are dealing with discrete. Let us say coin tossing problem. Tossing, say 3 coins. What is the sample space? H, 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 T, H. Sorry. Let us take 2 coins, right? The 3 has 8 outcomes. Let us just take 2 coins. Tossing 2 coins. And let us, the sample spaces HH, HT, TH, TT. And let X be the random variable that the number of hits. What is the probability mass function? The probability mass function is that it is equal to 1/4. Let me write it in a usual function form. So probability mass function is a real function. It takes real numbers and returns a number between 0 and 1. So the probability mass function is if X is equal to 0, it is 1/4 if X equal to 0. And if X equal to 1, it is 1/2. And if X is equal to 2, it is 1/4. And what else? This doesn't complete the definition of the function. And it is 0 otherwise. So if you take X equal to -1 or X equal to 100 or X equal to 1.5, for all those values, the probability mass function is 0. Now we are defining a function capital F of X such that, so this is the probability mass function. Now we are defining another function called the distribution function, probability distribution function, such that it is equal to the probability of X being less than or equal to capital X. And what does that mean? That is equal to sum of all values of the probability mass function of xj's such that xj is less than x. Right? So sorry for this. It should be. So the distribution, so this is also a real valued function. It takes in a real number and returns a real number. And the how is it defined? What is the probability of a random variable being less than or equal to the given number x? So let us write the probability mass function here. So f of x, when x is less than 0, what is f of x? What is the probability of the random variable being less than 0? What is the probability? So 0, because you cannot have less than 0 number of hits. What is the probability of x being equal to 0?
1/4.
So 1/4. And what is the probability when x can lie between okay, let us just put it this way. So when x is less than 0, it is 0. When x is equal to 0, it is 1. When x is lying between 0 and 1?
0, sir.
No, that is the difference here. So when x is lying between 0 and 1, it doesn't mean that we're PM of x when x lies between 0 and 1 is 0. But what is f of x? F of x is the probability of x being less than a value x. So it is 1/4. X is a number between 0 and 1. What are all the outcomes with the random variable taking a value less than that? You have one outcome, right? X equal to 0
Yes.
is less than x lying between 0 and 1. Therefore, you have one outcome, and corresponding to that outcome, the probability is 1/4. So you sum all that up to that point. Similarly, when x equal to 1, what is f of x? It is 1/4 plus 1/2. So it is the probability f of x is the probability of the random variable taking a value less than or equal to 1. So random variable can take the value 0 and random variable can take the value 1. So these two are two different cases. So you can add them up, right? By the axiom 3 of probability. So these two are random variable cannot take the value 0 and 1 simultaneously. So they are disjoint events. So you can add them up. So here it is 3/4. And what is the value when 1 less than x less than 2? It is again 3/4. And when x is greater than or equal to 2, what is the value? It is 1. So this is the distribution function. So if you plot the probability mass function, it looks something like this. So the mass function will take values of when x is 0, it takes some value. When x is 1, it takes double the value. And x is 2, it takes this value. So this is the mass function, and this is x. And everywhere else, it is 0. And the distribution function will look something like this. When x is less than 0, it is 0. Let me use a different color. When x is equal to 0, it takes a value of 1/4 and continues the same value till 1. And when x is 1, it takes the value of 1/2 and continues the same value till 2. And when x is 2 or more, it takes the value 1. So this is f of x. So this is the difference between the distribution function and the probability mass function. This is for discrete case. Is that okay?
Yes, sir.
So the normal, so in civil engineering, the usual one of the common, even for gate, right? So in gate, when we do transportation engineering, when we do traffic engineering, the next session, we'll see the Poisson distribution. It's a discrete random variable. Poisson. So whenever you're, and this is applicable when we are counting the number of vehicles that can come in a given interval of time. Suppose you're waiting on the road, and we are looking at the probability of, say you're waiting for a bus or some, okay, leave buses because they are scheduled, but you're waiting on a random highway and you're looking at what is the probability that in the next 30 minutes, I will encounter at least 3 or 4 vehicles passing through this point. So that is given by a discrete. The random, what is the random variable there? There, the random variable is the number of vehicles that pass through the given point in 30 minutes. So that is the random variable. The random variable is discrete. You cannot have 1.5 vehicle passing through it. So only for integral values, you have a probability defined. And how we define the probability is using Poisson distribution. What is the distribution? What is Poisson distribution? It is exactly f of x, corresponding to uh, every number, right? X can take only discrete values. 0 vehicles can pass, 1 vehicle can pass, 2 vehicles can pass. And corresponding to that, the probability mass function. So let me put it here. Yeah, discrete distribution. So let us look at this experiment of waiting on a highway. And count the number of vehicles in, say, 1 hour. So the random variable x can have no vehicle, you can have 1 vehicle, you can have 2 vehicles, you can have many vehicles. This is a discrete random variable, and we have a probability mass function. Let us denote this by small p of x. Hello, was it audible? There was some network issue.
Yes, sir. All the best.
So we'll denote the probability mass function as small p of x. What is small p of x? It is the probability of the random variable taking the value x, and that is denoted and that is given by a Poisson distribution, where that is given as mu power x e power minus mu divided by x factorial, where mu is the average arrival rate. or you can say average occurrence rate. So this is a probability mass function. So this is called the Poisson distribution. Okay, so this is the Poisson distribution. This is yeah. So this is one example of a discrete random variable. Now let's go to the next part, which is the continuous random variable, where we are throwing stones and we are seeing where it lands. In this case, suppose you know that the sample space and the domain of the random variable and the range of the random variable is like it has uncountably many elements. It has uncountably many outcomes. And suppose I say that the stone is equally likely to land in this place. Suppose I'm throwing the stone and I say between 1 meter and 2 meters, the stone is equally likely to land at every point. Now there is a paradox, right? So if I say the stone is equally likely to land at any point in 1 less than x less than 2 meters. What does that mean? That means that p of the random variable being equal to x equal to 1 is equal to something, say some s or p. P of x equal to 1.1 is p, and so on. So at every point it is p. Now suppose we just take some n number of points. We say there are n number of points with probability p, and all of them are equally likely. So the total probability should be equal to 1. But how many points are there in a given interval? There are infinitely many. So n tends to infinity, which means the probability p tends to 0. Now you have a paradox, right? It means that the probability of x being equal to a given value x is equal to 0. So this looks like the stone cannot land in a given point, but the stone has to land at some point, right? So that is the feature of the continuous distribution. That is not an issue. That is basically because we are defining probability in this way, it turns out to be having 0 probability for every individual point. But if you take the so what is the how do we resolve it? So the problem here is the random variable is not a countable quantity. So random variable is a measurable quantity, not a countable quantity. So the question we should ask is not that what is the probability of the stone landing exactly at a given point, because that there are infinitely many such points. The probability is very small or close to 0, almost 0. Therefore, the question we should ask is what is the probability of the stone landing between, uh, say 1.5 to 1.6. You take a small interval in that. You take a small interval and see and ask the question, what is the probability of the stone landing in that region? Suppose I divide the area into 10 intervals and I say the stone is equally likely to land in each of the 10 intervals. Then what is the probability? Then I can say P of x 1 less than x less than 1.1 is equal to P. The probability of the stone landing between 1.1 to 1.2 is P. And I have 10 such things. Therefore, the probability of the stone landing between any x to x plus 0.1 is equal to p. And there are 10 such intervals, therefore p is equal to 1 by 10. So this is the difference between continuous random variable and discrete random variable. In the case of discrete random variable, you can ask the question, what is the probability of the random variable taking exactly a given value? And that is answered by the probability mass function. In the case of continuous random variable, you can only ask the question, what is the probability of the random variable lying between two different values? Say, what is the probability of this lying between x and x plus dx? And for that, you have an answer that is given as f of x times dx. So now I divided the interval into 10 parts. I can also divide it into 100 parts, and I say that the stone is equally likely to land in each of the 100 intervals. I can divide it further into 1000 parts, and I can say that the stone is equally likely to land in each of the 1000 intervals. So I hope you're getting you see where I'm getting it, right? So if I have an interval, the stone, if I ask you the probability of the stone falling uh, at a given point, what does it mean? It means dx is equal to 0. It has to be x equal to x, so the probability is 0. But if I divide the interval into two parts and I ask what is the probability of the stone falling here, the probability of stone falling at this point is 1 by 2. One of the two cases. If I divide it into four parts, it is 1 by 4 in each of the values, each of the things. So similarly, the probability of the stone falling, if I divide it into 8 parts, each of the part has 1 by 8. So each of these part has a measurable length, which is L by N. So instead of defining the probability, we define what is called the probability density function. So for a uniform, if I say the stone can fall anywhere in between, so here it is 1 by 2, here it is 1 by 4, here it is 1 by 8. And what is all this? This is equal to L by 2 divided by L. The size of the interval in which it is falling divided by the total size. Here also, if you see, it is L by 4 divided by L. Here, what is the probability? It is L by 8 divided by L. So instead of looking at the number of, so this is an event. What is the probability of x belonging to the interval small x to small x plus dx? This is an event. And how many outcomes are there in each event? There are infinitely many outcomes. But instead of looking at the number of outcomes in A divided by the number of the size of the sample space, you're looking at the size of the set divided by the size of the sample space. So here the size of the sample space is L. If you measure the total length, it is L. If you measure the length of this event, it is L by 2. So this is how we define it. Therefore, in the case of a continuous random variable, we define the probability of x less than or equal to capital X, the random variable taking a value less than or equal to small x, is given by a distribution function. So this is why we define the distribution function f of x, which is given as integral minus infinity to small x f of x dx. So nothing. I'm just removing the previous inequality. If I remove this, what does it mean? It means it is the lower limit is minus infinity. Therefore, every dx, the probability of x lying between x to x plus dx is f of x dx. But now I'm summing all such probabilities from minus infinity to the given value. So the probability of the random variable taking a value less than or equal to a given x is given by the distribution function, which in turn is an integral from minus infinity to x f of x dx. So this is called the probability density function. It is not the mass function, it is density function. And this is called the distribution function. So a random variable which admits this kind of a representation is called a continuous random variable. And what are the examples of a continuous random variable? We just this problem, right? We can have So, or you can also have this, you can have a target board like this, where you shoot arrows onto it. So obviously we know the probability of shooting an arrow within the smallest circle is less than shooting an arrow into the biggest circle. That is why, you know, the points, you will have 100 points for the innermost circle, say 20 points for the outermost circle. And that is dependent on the probability. It is very easy to shoot outside. It is very unlikely to shoot in the innermost circle. But how can we define a probability? We can take the area of the circle. We can take the area of the smallest circle divided by the uh, say this full area. Then the area of the second circle divided by the full area. That will define the probability of the arrow landing in that. So this is how the continuous random variables are defined. And one of the common examples for continuous random variable is the normal distribution. So, so the normal distribution has a, so same thing. So the probability of a random variable taking a value less than or equal to x is given by a distribution function, which is defined as an integral from minus infinity to small x, f of x dx. So x is in the here, let me put it as f of y dy, because x is in the limit. And here f of y is given as 1 by sigma root 2 pi exponential of minus x minus mu by sigma, here you have the whole square, where mu is called the uh, mean, sigma is the standard deviation. So this you all know. And again, this has a very common example in civil engineering. What is it? How do we define the strength of a concrete cube? We call something called characteristic strength of concrete cube, right? So the random variable in that case is the strength, compressive strength, uniaxial compressive strength in say new MPa. And the strength can take any value. If we say it can take 20 MPa, 20.1 MPa, 20.01 MPa, it is a continuous random variable. So that is the so mm, that is the random variable. Even if you cast a cube with all the controls, if you test 3 or 4 of the same sample, their strengths will be different. So the probability of strength less than or equal to small x is equal to, so the strength that is not exceeded, that is equal to some value p, right? So this strengths, the uniaxial compressive strength of a concrete cube, that is assumed to be normally distributed, where normal distribution is defined like this, and the function f of xy looks something like this. So the peak is where mu happens. So this is the median, this is the mode, and this is the mean. And standard deviation is a certain measure of spread. And what you call the characteristic strength is the probability of the strength which is not exceeded by 95% of the cubes. So suppose we test 100 cubes, 95 of those cubes should not fall below a certain strength called small x, which is called the characteristic strength. So if you say M20, it means upon testing a large number of cubes, the probability of a random cube taken from that lot, the probability of the strength of the randomly selected cube not lying less than uh, this specified value is 95%. With 95% certainty, I can say that if I randomly select a cube out of that, if I randomly cast a cube and test its strength, the probability of the strength of that tested sample not being less than 20 is 95%. So that's how you define a characteristic strength of. And so x is assumed to be normally distributed. So x is the uniaxial compressive strength of Q, and x is the characteristic. So this is just an insight into how these continuous distributions work. This we don't have time for today. I have many problems. So I think Maybe we'll do one thing. I'll post it in the group. You can go through them, and we'll discuss the solutions in the next class. I'll upload it in the Google group. You can try solving them. These are all from the previous year gate only, so it will be helpful for you. And we'll discuss the solutions in the next class. Is that okay?
Yes, sir.
Yeah. Is it okay for the others also? I think Dharani is okay. Others also okay.
Yes.
Yeah. So that is almost the end of random variables. There is just a few more topics, like how to compute the mean and standard deviation of a random variable. Uh, and regression analysis is not so difficult. That is easy only. So tomorrow, just like how we looked at stability today and got into random variables, in the next session, you say, so these are some questions. For this to be a valid probability density function, maybe I can discuss how to do it. So the area between, so the sample space is minus infinity to, so the sample space is mapped to the real line. Probability of sample space should be 1, which means the probability of x belonging to the real number should be 1. So what does that mean? Probability of x less than or equal to infinity should be 1. And this is given as, we know, integral f of x dx. If you replace it by small x, it is minus infinity to x. And in the place of small x, you have infinity. So this should be equal to 1. So this is the idea you need to use. If f of x is a valid probability density function, then if you integrate it from minus infinity to infinity, you should get 1. So you can see, so that is the trick here. That is a hint. You can solve this question. Similarly, the others also you can solve. These are just similar to those. You give an attempt. I'll upload the presentation in the with some more probability questions in the Google group. You give an attempt. We'll discuss in the next class. So, is there any doubt in the in what we discussed today? I'll wait for a few minutes. If you have any doubts, you can stay back. Yeah, I'll wait for a few minutes. Otherwise, you can. You can also suggest topics for the next sessions, right? Because now almost all topics are repeating by other scholars. I'm basically from structural background, so the topics that I've planned for is, one is traffic flow. After that, open channel flow. If you have any other topics, you can tell me now. You can also post in that group, because anyway now it is repetitive, right? Other scholars would have already covered some of the topics. If you want me to cover something, you can tell me. I'll note it. Because now the gate exam has come closer. Only 3 more months left. 2 more months left. So if you have any particular topics, you can do.
Thank you, sir.
Yeah. Okay. Thank you.
So regarding topics, I think we should focus on problem solving. We will upload our doubts on Google group, and then in the next class you can discuss our problems. Like today you discussed first 30 minutes, you discussed the problems of one student. Like similarly we
Yes.
can do, because all the topics are covered. So
Yeah.
before only we'll paste, we'll upload the questions on Google group.
Okay.
And then this is how. So today's
Yeah,
session.
sure. Yes. Sorry, you were telling something?
I was saying that today's session you can end.
Yeah.
We'll post our doubts on Google group. Thank you.
Okay. Yeah. Thank you. Shaili, is there any? Okay. I hope everything is clear. So thank you for attending. So we'll take up this work plan, upload the doubts in the Google group. I'll take up those questions and we'll discuss it in the next class. Thank you. We stop sharing and I can stop the recording.